Hey everybody, welcome back to another video on chemistry. Woo! Okay, so today we are learning some stoichiometry. This is going to be hopefully a very helpful review for our quiz tomorrow. For anyone who had the test today, I am so sorry that I didn't get it. Oh, hello. I cannot speak English. I'm so sorry that I didn't get the video out sooner. I've had a super duper busy week. But yeah, for my Blue Day friends, let's go ahead and get into it. Okay, so the topics on the quiz, right? Net ionic reactions, molar mass converting from moles to liters, grams, and molecules, two-step stoich going from grams to liters, etc., limiting reactant and percent yield. That is Ms. Rectanus' words, not mine. Okay, so let's go ahead and start with something simple. Let's go ahead and start with some molar mass practice problems. So these ones that are from the worksheet are a little bit blurry to see, so I did write them here if you need those. I'm going to suggest that everyone pause the video right here and go ahead and try these problems yourself. And then we're going to go ahead and get into it. So I'm going to give you a minute. You can go ahead and pause, and then we're going to go over all these. All right. So let's look at this. And remember, just for this one, we're going to just need our periodic tables. So I am going to do, let's just say, these first three, and then I'll do the rest of the ones off camera, and we'll come back and discuss, because this video is going to end up being super duper long anyways, because there's like limiting reactant, net ionic equations, a ton of stuff. Okay, so lithium iodide. Let's just look for our molar mass of lithium, which is 6.94 on the particular periodic table that I'm using. And then iodide, which is 126.90, and then just use our calculator and add. This one was really easy. I think this part is definitely going to be the easiest part of the test. I mean, obviously. Okay, and that gives us a total of 133.84 what? Grams per mole. I'm going to emphasize this. Grams per mole is what we use for molar mass. 133.84 grams per mole. Okay, let's look at this next one. Lead. I don't even know what compound that is, but it's lead something. But we don't really need to know what the compound is, because we just look at the particular elements within it. So there's lead. Let's go ahead and do lead, if I can find it on my periodic table. 207.2 plus C, carbon is 12.01, and then we see oxygen here, right? So on the particular periodic table that I'm using, it just used 16 flat. So that's what I'm going to do. So 16 times 4 is 64, because it's, remember, 1 of oxygen would be just 16, but since we're doing 4, it's 64. So then let's go ahead and add that up. 207.2 plus 12.01 plus 64, which gives us a total of 283.21 grams per mole. One more, and then I'm going to do the rest off camera, and we're going to briefly discuss. Okay, so let's look at this one. Magnesium hydroxide. Okay, so let's just look at our magnesium real quick on our periodic table, if I can find it. Magnesium, okay, 24.31. And also, you could put units next to these, because it is technically grams per mole, because it would be like the molar mass of like the singular compound. But I'm not doing that. Just make sure in your final answer that you have it. If it helps you to do it in your equation, do whatever. But remember, when you have your final answer, you need to have units. Without units, it means nothing. It's not, you know what I'm saying? It's not what it means to be. So we look at our hydroxide. Because magnesium has a 2 charge and hydroxide has a -1 charge, obviously the magnesium is not affected, but the hydroxide is, right? So now we see this. Instead of just having 1 oxygen and 1 hydrogen, it's 2 oxygens and 2 hydrogens because of that 2 charge that ended up crisscrossing. Okay, so 32 because we have 2 oxygens, and then hydrogen would be times 2, so 1.01 times 2 is 2.02. And then the total for this is going to be 24.31 plus 32 plus 2.02 is a total of 58 0.33 grams per mole. Okay, I am going to pause here real quick and I'm going to do the rest off camera, and then everyone who did the rest of the problems can check their answers. Okay, so I went ahead and I finished this worksheet. So everyone go ahead and check your answers, and let's just go ahead and go through this rather briefly. So this one is 200 for number 4 for potassium phosphate. I don't know, probably. 212.27 for ammonium phosphate. Sure, let's go with that. 149.12 grams per mole. I don't know, whatever this is. The C6H12O6 is a total of 180.18 grams per mole for iron sulfate. Sure, we'll go with it. 399.91 grams per mole for sodium phosphate. It was not, I don't know. Sodium and phosphorus. It's 99.94 grams per mole. Then for silver fluoride, it's 126.87 grams per mole. And for ammonium acetate, I believe it is, at this bottom one, is 77.1 grams per mole. And so if you used a different periodic table than myself, you probably have slightly different answers. But if you get like roughly these, it's okay, because like different periodic tables will say different things. Okay, next let's go ahead and move on to net ionic reactions. I did not print out anything to help with like converting from moles to liters to grams to molecules, etc., because I couldn't really find an effective worksheet that encompassed all of those in one, and I didn't really feel like putting out 3 separate worksheets. So I already have 3 more worksheets to go over with y'all. So I just recommend reviewing that on your own. Remember your mole maps, make sure you write those down. And yeah, just do some brief practice on that, but it should be okay. Okay, so here we are again with another worksheet. So we're gonna be doing net ionic equations. So it gave us like the compound names and stuff, and like we had to name it, then balance, and that would have been a lot. So I went ahead and I already did that. So we wouldn't have to worry about it because this video is going to be pretty long anyways, as you guys can probably tell. And I don't feel like keeping you guys here for 85 years. So let's go ahead and get into it. So if we remember how to do our, hello, could I speak English? That'd be great. Our net ionic equations or reactions. Oh, and I just dropped the paper that I needed. That's beautiful. I'll grab that later, whatever. Okay, so we did this a while ago. I feel like we did this like at least 2 or 3 weeks ago, but nevertheless, let's get into it. So let's look at our strontium bromide, potassium sulfate to strontium sulfate, potassium bromide. So obviously this reaction works because it forms something solid. And I'm not sure if we need this for the test, but I think you guys should recall our solubility rules. I would keep your little pamphlet with you during the test. I don't know if she has you determine what's soluble, what's aqueous, etc., but it would probably be beneficial just in case to have it on you. Okay, so let's go ahead and do our ionic equation. The ionic equation is the really, really long one, as I'm sure you guys can remember. So let's go ahead and get started. Okay, so strontium is Sr, that's only one of them, and it is a 2+ charge, and then it is aqueous. Put our little AQ there. Then we have bromine 2, because there's a 2 there, so 2Br with a minus charge, which is also aqueous. Okay, and then let's go ahead and add. Let's get to our K2, so 2K with a plus charge, AQ, and plus, and then SO4 with the 2 minus charge, which is also aqueous, and then put our little arrow here, and then it's and remember, when we get something solid, we keep it solid. So for our strontium sulfate, since it's solid, let's just keep it strontium sulfate. SO4, which is a solid. Then let's add our potassium bromide. So 2K, which is a plus charge, aqueous. Then plus 2Br, so minus, aqueous. So that is our full ionic equation. I don't know if my little worksheet was off frame. I'm sorry if it was, but that is our full ionic equation. It seems like a lot, and I'm going to be honest, it is. It is. I don't understand why this was on the test, but nevertheless, it is, and we need to know how to do it. It's really long and complicated, but it's easy. It just takes a lot of work, but in all reality, it's easy. So once you write this out, all you have to do is you have to write the things that created this new compound. For the net ionic equation, it's only the things that like created the solid. So let's underline our solid here, right? So strontium sulfate. So I'm going to underline sulfate too, and I'm going to underline strontium too. So all I have to write for this net ionic equation is Sr2 plus Aq. So just essentially what I wrote here, then plus SO4 2 minus, which is aqueous, and then put my little arrow here, turns into SrSO4 solid. And that's it for our net ionic. That's it. That's all we need to have for our net ionic. And okay, so I did the first one. I gave us an example. I'm going to go ahead and finish the worksheet, and then I'm going to come back and we're going to go over it briefly, just like we did the last one. And then after that, I believe the next worksheet I have is percent yield. So yeah, let's get into it. Okay, everybody, I'm back. So I went ahead and I finished this worksheet. I mean, just look it over if you want to pause the video. I'm not really sure. I've like been having video problems, like where like my camera's blurry or some stuff like that. So yeah, I would just pause if you can, and make sure. I feel like with this type of chemistry, it's pretty self-explanatory. It's just really long. So I did the first example with you guys, so that's pretty much how you do it for like all of them. It's really easy. But yeah, if you want to go ahead and pause the video, the only thing I am going to note is for this bottom equation, number 5, the one that's lithium hydroxide, barium chloride, lithium chloride, barium hydroxide, it's no reaction. If you look at my net ionic, I don't know if you can't read that. I wrote no reaction. Why? Well, because both lithium chloride and barium hydroxide are aqueous. If they're both aqueous, how are you going to tell if there's a reaction? So that's just something to remember with our net ionic. If they're both aqueous, it just won't work in the end. So, yep. All right, next we are going to look at some some percent yield. All right, everybody, I'm back. That took a while. But anyways, I went ahead and I finished this worksheet. So instead of me spending like 8 hours here trying to figure out what the heck I'm doing, I can actually teach you guys what the heck this means and what is going on. So me personally, I think percent yield is relatively easy. My thing is, I feel like limiting reactant and like excess reactant, I feel like that's the hard stuff. But there's a worksheet on that after this. So yippee, let's get into it. So first, I just had to write the balanced equation. So pretty simple, pretty self-explanatory, just naming and then balancing. Yeah, so if you have any questions on that, I do have a video on balancing equations as well. Then naming, we learned that like first semester, so that should be pretty okay. Okay, so let's look at this second problem then. If 36 grams of tin 4-phosphate is mixed with an excess of sodium carbonate, how many grams of tin 4 carbonate will form? Okay, so my thing is, whenever you see a number, underline it or make sure that this is going in your first box here. And I'm gonna write a formula. I'm gonna grab a separate sheet of paper and I'm gonna write a formula Actually, I want to write it on my periodic table so I can show you guys this formula that you want to see. So whenever you see this number, if you see a number, this is always key in problems like this. So if you see a number, I'm going to say it again, like highlight it, emphasize it in some way. And then another thing to highlight or emphasize in a different way though, how many grams of blank is formed or something similar like that. That is something I would box. So I box the thing that I'm looking for and I underline the thing that I'm given in a number amount. Okay, and so once you get this thing in the number amount, you put this here. Whenever you see their number amount, put that here. So 36 grams of tin for phosphate. And then your next part is always mole, especially if you're going between moles and grams. And then you put the molar mass of this. And then we're going to do our mole ratio. So box on top, right? So it's 3:1. So bam and bam. Pretty self-explanatory. That's why I do the box and the underline, because that's the way that Miss Rectanis taught, to do the box on top. Okay. And then the next part is whatever the other substance that you didn't get the molar mass of. So tin for carbonate, do the molar mass of that here and then put mole, and then you can calculate. And I got 35.03 grams of tin for carbonate. And so that should be, I did check that, that is correct. It might be a little off depending on the periodic table you use, but that's what I got. And then from that, I went to the next thing and have our percent yield equation up here. So actual yield over theoretical yield times 100. So we're given 29.8 grams of it was actually formed. And this is the theoretical yield. This is the theoretical yield up here. That's what we found here. So 29.8 divided by 35.03 times 100 is approximately 85.07%. And I also checked this is correct. So remember, I would write this down somewhere on your periodic table. This is very helpful. Our last thing is down here, if you guys can see, let me just move this slightly. If 7.3 grams of sodium carbonate are used in the reaction and the result in a 74% yield, how many grams of sodium phosphate will be formed? Okay, so like I said, whenever you see a number, this is always key. Like, I automatically take notice of this. And something else, like I said earlier, what I take notice of is how many blank, how much blank, you know? How many grams of sodium phosphate will be formed? Box that. That's what we're looking for here. So I'm going to start out my equation, right? So I put 7.3 grams of sodium carbonate. And then I put my mole, because you always put the mole next. Then the molar mass of sodium carbonate. Then I do my mole ratio. So box on top, sodium phosphate has 4. And then sodium carbonate has 6 in our balance equation. Then we're going to put the molar mass of sodium phosphate here over mole. But then there's an extra step to what we usually do, right? Right. So I don't think this will be on the test. However, it's just what was on the worksheet. So that results in a 74% yield. Okay, 74 over 100. This is just the percentage of the yield. So just put 74 over 100, but I don't really think anything like this will be on the test. So just remember your formula for this, which I will also write down and show you guys. Okay. So I did the math for that, and it's approximately 5.57 grams of sodium phosphate. Okay, so next I'm gonna grab my periodic table, and there's a lot of notes on this already. So I'm actually gonna flip this to the back, because this is probably the one this is the periodic table I've been using for like molar mass and stuff like that, and probably the periodic table that I'm using more often compared to the back. Okay, so I'm gonna write this equation. And it's not even an equation, it's more so a formula. Okay, so I'm gonna say amount, given grams amount. So when, you know how I said, sorry, let me just erase this thing here. I said if you see like a number like, I don't know, 7.3 grams, like there was for the last, I'm actually gonna erase that because there's not enough room for that. But you know how I, given grams / units amount, like if you saw like 7.3, you automatically know that goes in this box. This is what I mean. Okay. And then mole, because that always comes next. Molar mass box 1. This is box 1. So I'm going to give it numbers. 1, 2, 3. And then this one is the mole ratio. Box on top. Other compound ratio. So that's what happened when we had like the 4 to 6. So I boxed the whatever we're looking for, and that went on top, and then the other compounds like amount in the balanced equation went on bottom. And then for the last thing, it's the molar mass of the box. So molar mass of boxed, and then over mole. So I hope this makes sense. So the given gram/amount, mole, molar mass of the box 1, I gotta number the rest of these, 4, 5, 6, 7, 6, 7, sorry, I'm on TikTok too much. So when we look at this might look a little confusing, but if we look back at this equation and just ignore this part, it will make more sense, right? Because you put the 7.3, the molar mass of this, the mole ratio with the boxed on top and the other compounds ratio on bottom, the molar mass of the other compound, which is the one that you're looking for, the box, the molar mass of the boxed over mole. There we go. That is the perfect ratio for a 3-step stoichiometry. All right, so next, our final thing that we're going to go over is limiting and excess reactants. So let's go ahead and get into it. All right, one more worksheet. Woo. All right, so what I went ahead and I did this worksheet because you guys would have sat here watching me twiddle my thumbs for probably like 6 hours because I would have been confused, and doing it on video stresses me out. So I went ahead and did this. So you'll notice these two problems look very familiar. It's because they were on our limiting and excess reactants worksheet from last week. So I went ahead and just redid them. This problem is different though, but it's the principle of it and it's practice. So let's go through it. So our first problem, it gives us the balance equation. How many grams of NH3 can be produced from the reaction of 28 grams of N2 and 25 grams of H2? So first, you have to find the limiting reactant. So, which is nitrogen. But anyways, so you'll set up your equation. So you start with, well, I did my nitrogen equation first. So I put here, nitrogen amount goes here. It's the same thing, the same formula that I told you guys earlier. Then you do the molar mass of N2, then the mole ratio. So your box goes on top because you're looking for NH3, so the ratio is 2 to 1. And then the amount of the box, the molar mass of the box, 17.04 over mole, and I got approximately 34.06 grams of NH3. I did the same thing for hydrogen, except just a little bit different because obviously the amounts are going to be different. So I had 25 grams, and then I put the mole, and then the molar mass of hydrogen, the mole ratio, so box on top, 2 to 3, molar mass of NH3 over mole, and then I got approximately 140.59 grams of NH3. With this, you want to find the smallest amount. So N2 is your limiting reactant, but the smallest amount you box. That's how much grams of NH3 can be produced from the reaction. Okay, and then when it's asking how much of the excess reagent is left over, okay, well, let's go ahead and do another equation. So plug in this is what you ended up with of the NH3. You plug that in here, put the molar mass of NH3 here, do your box on top because you're looking for H2 now, right? So you're gonna put 3, then the 2 because box on top. Then the molar mass of your box, so 2.02 over mole, is approximately 6.06 grams. That, however, we are not done. I want to clarify, we are not done. That is not our answer. That's how much was used by the reaction. However, this is not our answer because we started with 25 grams of H2. This is how much was used. We're going to subtract 6.06 from 25 and get 18.94 grams of excess H2. Okay, let's go to our next problem. Number 2, considering the following reaction. magnesium plus 2 HCl to magnesium chloride plus H2. What volume of H2 at STP, which I have no idea what that means, is produced from the reaction of 50 grams of magnesium and 75 grams of hydrochloric acid? Okay, so let's go ahead and do something similar to up here. Since we have two of these, we need to find out which one has the smaller amount. So I did it with magnesium, so 50 grams moles, molar mass of magnesium, the ratio. Then this might look a little different. I wonder. This is because it asks for volume. Volume is found in liters. So if you look at your mole map, you know that in order to find liters, you have to multiply by 22.4. And then over the moles, and I got approximately 46.07 liters of H2. This next one, 75, because I'm doing the HCl. 75 molar mass of HCl, the ratio, then the amount to get to liters, mole, and I got approximately 23.04 liters H2. So that is how much is produced. That is how much H2 is produced in the reaction of 50 grams of magnesium and 75 grams of hydrochloric acid. And that means that hydrochloric acid is also our limiting reactant. Okay, let's look at this last one. This last one is not going to be familiar because we did these two in a separate worksheet, but this one is different, but it's the same principle. Okay, so zinc and sulfur react to form zinc sulfide according to the following equation: zinc plus sulfur equals zinc sulfide. Suppose 25 grams of zinc and 30 grams of sulfur react. Which reagent is limiting? Okay, so we have to do our two equations again. So I set it up. 25 grams times the mole over the molar mass of zinc. Put the ratio 1:1. Then the molar mass of zinc sulfide over mole is approximately 37.26 grams. This next part, which is for the sulfur, 30 grams mole, then this is the molar mass of sulfur, the mole ratio, then the molar mass of zinc sulfide over mole, approximately 91.17 grams. So remember, we always look for the smaller one. So zinc caused the smallest amount to happen. Therefore, it is also the limiting reactant, which is the main purpose of the question. Which reagent is limiting? It's zinc, because it made the smallest amount in the reaction. Okay, so I really hope this video was helpful for you guys. Please study. I know I'm releasing this video late, and many of you aren't going to watch it until the morning. I'm so sorry. I would have gotten it out earlier, except I took a 3-hour nap when I got home from school. Yeah, I really hope this video is beneficial, that we comprehend this stoichiometry stuff. We understand some of the formulas. We understand what we're doing. And yeah, I wish you guys the best of luck on the test tomorrow. To my Red Day folks, I'm so sorry if you guys did not see this, or because you guys did not have this for your test. I'm so sorry. But yeah, happy studying. Good luck, everybody. Bye.